Our next speaker today is Seth Hardy from Lookout, who will be discussing their approach to rapid analysis of mobile malware. Seth?
Hi, everybody. So welcome back from lunch. My name is Seth. I'm a staff security engineer at Lookout on the research and response team. Lookout is a security company that focuses on mobile, so looking at primarily Android and iOS applications, phones and tablets. So get started. That symbol is different than was on my slides. That's all right. Private use. Okay, I have no idea what that is. So the purpose of the research and response team at Lookout is to identify and prevent current and future threats to user security and privacy. In general, we're looking at mobile malware. I personally have about 10 years of experience looking at malware, both from the AV industry and spending 4 years at a university research group looking at targeted attacks against human rights organizations. So it's not just malware that we're looking at, it's all current and future threats. This is pretty broad, so I guess let's take a look at some of the things that you might expect to see. One thing that we deal with a lot are financially motivated attacks. So in this case, this is a banking Trojan, bankun.b. You can see in the left that there is a banking application, looks exactly like this Korean bank. When you load it up, you see the splash screen for that bank. And what happens in Korea is that these banks often have one-time authentication pads that require users to authenticate with codes over SMS. So in this case, this is not a legitimate banking application. It's actually a Trojanized one that will steal your authentication codes and let an attacker log into your bank, steal all your money. Another thing that we might see, ransomware. So here's an application that pretends to be some sort of a scanner, and it will pretend to look at all the apps on your phone and then pop up a warning from the FBI, supposedly, saying that it's found all sorts of nasty stuff on your phone, and it's got this seal and some signatures, so it's clearly legit, right? Some of these apps will actually even turn on the front camera on your phone, so it'll have a picture of you right next to the "we've detected child porn on your phone," which is really scary, which brings us to the next screen, which is send us money and maybe everything will be okay. And sometimes, if you send them money, everything is okay, but usually you send the money off to Russia or wherever it's based out of, and your phone is still unusable, and there's nothing you can do. So this is ransomware. The family name is Cold Brother. The variant is A. This is exactly what it looks like. If you get this on your phone, it's actually pretty trivial to get rid of it if you know what you're doing, but unfortunately, most people don't. We also deal with things like click fraud. So here's an example of an application sending network traffic that is designed to bring up ads from search engines and click on things in order to cause defrauding the advertising networks by artificially clicking on links. So in this one, you can see that it's sending an HTTP GET request to a command and control, a C2 server, and the information that comes back includes a URL to a Baidu website with a search for that phrase in Chinese. And I believe this one has to do with news articles about flight attendants wearing certain kinds of clothes. I don't know exactly what's going on there, but the idea is your phone will then load that URL and poke at things in order to try to get money away from the ad agencies and into the pockets of the people who made the malware. These are some of the slightly more nasty ones. I guess not so much the click fraud, but the ransomware in particular. We also deal with less trivial things, or more trivial things like adware, and all sorts of the long tail of surveillance and state-sponsored surveillance and other nasty things. But one thing in common here is that these are different types of malware. They do different things. They can be fairly easily identified, and we need to block them all. That's the theory. In practice, Ted Goetz is our team mascot, unofficial. We get a lot of input from people whose phones are not working properly. And one quote kind of resonated with us: "My hand phone always be malware." This was on Android. My hand phone always be malware. So I'm going to be talking mostly about Android here. We handle iOS differently because of the way Apple locks everything down, both in terms of app distribution through the App Store as well as app encryption. So I'm just going to be talking about APKs here. So what do we do on research and response? Well, first, Lookout tries to acquire the world's APKs. So we try to collect everything we can. And this means through app stores, this means through user submissions, this means through web crawlers. Any way that we can find a way to find more applications, we will automate that, write crawlers, and pull them in. We then put them into an automated analysis pipeline. So we will decompose the APKs, pull out the classes dex file, we'll decompile it, we'll pull out the assets, we'll take a look at the signatures on the APK. We'll run the application through a dynamic analysis environment where the functions are hooked and we can collect more data on what it's doing. We'll look at the permissions in the manifest and try to figure out what is this thing requesting so that we can compare what it's asking for versus what it does. And then we have to identify and classify these samples. So we want to know the type, we want to know the family, and we want to know the variant. And then once we have all of the identification done, we need to provide coverage, not just for the apps that we are seeing in the moment, but against unknown apps that are related, as well as any future apps from that same family or variant. So some numbers, more broken icons. Right now we have, the number here says 17 million. Since these slides were made, we're much closer to 20 at this point. 60,000 new apps per day is an average. Sometimes we'll see well over that. The company as a whole only has just over 300 full-time employees. And my team, the research and response team, the number there is 11, but it's more like 10 and a half because one of those people is an intern. Sorry, Emily. So 11 people can't handle 60,000 plus apps per day without having some sort of automation. So I'm going to talk about how we do automatic classification of malware. If anybody understands this slide, you'll understand that most of what we're looking at is, in fact, malware. And we want to break it down into type, family, and variant. So the types are determined by what the malware does. So examples that I showed you before, if it obstructs use of the device by drawing something over the screen and gives you an opportunity to attempt to unlock it, that would be considered ransomware. However, if something draws over other apps and is not designed to completely obstruct user interaction, then that could be adware. That could be something else. So we want to look at what apps do to figure out what their type is. We can do it manually, but we want to automate it. And the way that we handle this in practice is through looking at the capabilities and the actions. So capabilities include the permissions. So if something is accessing your SMS messages and it asks for permission to send SMSs, then it's quite possible that this is an SMS forwarder. We need to look at the actions as well, because if you have a game that does in-app purchases, this is often done through SDKs that use SMS for payment. So just because an application is looking at your SMSs and possibly aborting the broadcast that pops up that you got an SMS, this might not actually be malicious. It might not be trying to hide something for anything other than the user experience. So we need to look at all of the capabilities and the actions in order to figure out what the type is, and then we use a machine learning system to give us hints and do automatic classification. I'm not going to be talking about that here because I only have 10 and a half minutes left and I have other things to talk about. Families, the next level of granularity, they're related samples from the same source. So in this case, we are looking at common code, whether it is a piece of ransomware or an SMS forwarder, if it's coming from the same author and doing roughly the same thing, then it's probably going into the same family bucket. It doesn't depend on what it looks like from a superficial standpoint. So if the app, one of them might say that it's a battery saver application, another one might say it's a porn application, but in both cases, when you load it up, all it's doing is sending SMSs to a premium shortcode to get money from you. If the code is the same underneath, it's doing the same thing, and it's from the same author, it's in the same family. And the family analysis here that we do is also for the purpose of doing actor tracking and attribution. This is a terribly difficult problem, and a lot of companies will try to sell you the world for threat attribution and actor attribution. We're not making any grand claims. We're just trying to figure out where things are coming from so that we can be more useful and efficient in doing takedowns and protecting our users against these families of malware. Variants are closely related samples within the same family. So what we're doing is we are defining versions of that family by reverse engineering the applications. We don't have the source code. We are arbitrarily picking cutoff points for saying this is version 1, this is version 2, this is version 3. It's not always linear. Sometimes you will see forks and splits, and then sometimes code bases remerge. But we're trying to pick a code distance where we say we think this has changed enough to warrant calling it a different variant. Maybe it changes a protection technique. Maybe it communicates with the server differently. We classify it as a different variant and start associating things with it and move on. The main way that we do this is through code distance. We have a number of different metrics where we will analyze all of the code in an Android application from the classes.dex, and we will look at it on a class-by-class basis using a fingerprint that we decide based on a representative application. And we can see the distance from the original based on the number of metrics that we have. So in this case, 2 different applications. They have different package names, different icons. They have completely different resources and associated material in the APKs. But if you look at the code similarity, you can see that these are the same code, the same classes.dex, same code in these classes underneath it all. So 1.0, 1.0, 0.9999. There are no similar classes. There are no missing classes. So these are the same thing, even though they look completely different. And Shidun is a recent piece of, it's being used for adware and ad distribution, but it has the unfortunate side effect of rooting your phone and installing itself in a way that will persist even across a factory reset. This is malicious, it's really terrible, and all they're using it for is serving ads right now, but it's still pretty terrible. This has been a big problem because we've been seeing a lot of new malware families and variants starting to use this technique. So here's another example of an application that is in Shidun.a. So same type, same family, same variant. In this case, the APKs, they look the same. So the application name is the same, the icon is the same, the application that it pretends to be is the same, but the code is starting to drift a bit. And you can see that two of the classes that we index on now match, and the other ones got about 90%, 97%, and 90% again. So these are starting to drift, but it's still within the bound that we consider this the same variant. Here's another one. So Shidun.a versus Shidun.gen for generic. The APKs are fairly similar, but the package names have changed a bit. This is a different variant because you can see only one class matches now. The other ones have a lower score for similarity. So 79%, 59%, 77%, and one class is missing from one of them. So this would be enough to call it a different variant, make a new code fingerprint on it, and move on. So indicators are how we find samples in order to start doing this analysis with the code distance metrics. So you can start with dumb signatures. Everybody says that mobile AV is just looking at package names. We do that with a million other things, but that's the one thing that people always remember. We also look at the program features, such as the services, the receivers, the capabilities, the permissions, and we take the activity through dynamic analysis, such as the command and control servers that they contact, activated attempts, and we take all this information and we train up some machine learning programs, and we use it to make recommendations as to what the type is and possibly even what the family is based on how close it is to other things in that area. But we now have a pool of samples that we can look at that we want to put through this very quick automated sorting hat that uses code similarity. Variants, as I mentioned before, they're entirely defined and tracked based on code distance. So every time we find a new variant, we make a fingerprint or a code imprint on the relevant malicious code in it, define a threshold for maximum distance, how much we're going to let it drift, and then cluster it accordingly in order to completely populate the family and find all of the variants as well. Once we have all of this done, we can provide protection. We're not going to lose track of families because if you're making incremental changes to code, and malware authors generally do this, they are software engineering shops. Sometimes they even have customer support hotlines for when your malware isn't working properly. We don't lose track of families because we're tracking the code that they're using and watching the incremental changes. This can work even if everything else changes. Automatic detection this way based on code distance totally works. Last month, 208,000 applications were marked as malware just by looking at code distance with no follow-up manual action required and 0 false positives. So this entire system isn't 100% foolproof, but it's pretty good once you have the tracking system in place. One way to get around it is through packers, cryptors, and obfuscators, ways of hiding the code. So in this case, we have to do the extra step of figuring out how to identify the packers, which we can do using these techniques, and then make an unpacker and an analysis engine so that we can then take the decrypted APK and put it into our pipeline. Once all of this is done, we do some clustering. So we have a tool called Pleiades, which does mass binary similarity clustering. So it'll create a code index for each sample, and just on the relevant malicious code, and then create a pairwise similarity matrix. So everything in the cluster, or in the group of samples that we want to cluster, will be given a code distance from every other sample. And we do this by pushing it all up to AWS and having it crunch away there. Once that's done, we can cluster the results, and this can be tuned in a way so that we can define the variant drift parameter, as well as choosing minimum points per cluster. We can then cluster the clusters and look at intercluster similarity to figure out which variants are most closely related. We get all this data out of it, which we can then use for further analysis. And here is a visualization of some of the data that we've had. Each color is a different variant. This is looking at Shidan and related samples. This is done over time, so this is when they're first testing it out, and more samples arrive. And zooms out because we're about to see a major campaign launch. So all of these samples that are showing up very rapidly are from individual campaigns. And each of these clusters, again, is an individual variant. The yellow lines are nearest neighbor. If we enable traditional heuristics, we can see more relations to them, but even without it, we can still see which variants are most closely related. And if you look at the package names, you can see that in each cluster, they're generally related to each other by theme, which implies even more that each variant is an individual campaign of this malware being launched against our users. This was used for finding connections between these three families, SchuaNet, ShiftyBug, and Shidan. Too many S names makes it confusing. We're not going to do that again. But these are all the adware Trojans that will root your device and install itself in the system directory so that it persists after a factory reset. We were able to figure out all these connections based on our ability to look at all these other samples and see what the code distance and similarity is. And what we're doing next, trying to get more application features in for classification, especially getting type and family done automatically. We also want to do code distance metrics without fixed starting points. So rather than needing those indicators, we have a system where we can take any application and look at its neighborhood of applications, like LinkedIn style, see what it's close to, and catch things that way. And we can do this at the per class level, not just for the entire binary. So that's all I got. Thank you very much for your time. And yeah, thanks.